All right. Good. So I'm doing this project here, C510, quantum computing. We're going to do a couple of very simple calculations so you get to see what the quantum computing process is like. And so we're going to use an online Python environment that works much better than trying to install these libraries. So you go to this Python Anywhere and create an account, although you could probably use Google Colab too. But I did it this way. I tested it earlier today and it worked. So I made a free account. And now you can make a new bash console. So it's very much like Google Colab. You have a Python, a bash environment here. Now, all right. Now we're going to have to install. Oh, I should have made a. I should have made a. Oh, right. First, we have to install stuff at bash. That's right. So you give it Python -3m pip install upgrade pip. That's right.
Is Python Anywhere give you powerful machine or something?
No, it's just the only one I knew about when I wrote this project a couple of years ago. I imagine GitHub Copilot is probably better. But I just, this is the one that I wrote a project on and I tried it earlier and it worked. So I upgrade pip just as that's recommended before you install software. And then I install, this is what you need, the Project Q Python library, which simulates a quantum computer. So, all right. There it goes. All right. So once that's done, now we can make q1.py. These are the programs that perform simulated quantum computing. And while that's building, I can be talking about the program is here. So you import the stuff you need, which is measure, which performs a measurement, the main engine, and the quantum engine, which is what we're going to use. And we're going to create 10 times, we're going to create a qubit. When you first create a qubit, it's in state 0. And then we're going to measure it, and then we're going to print out the result. So it should just stay in the state 0, so it's not a big deal. It's still building here, apparently. All right. And I'll go down to the picture here. So the way to understand a qubit is the quantum equivalent of a bit, but it goes like this. This thing is called the Bloch sphere. Your qubit can be in a state of 0, and it can be in a state of 1, but it can also be anywhere on this sphere. And unless it's in this 0 or 1 state, if it's in one of these intermediate states, like this Y state here, then it has a certain probability of being 0 and a certain probability of being 1 when you measure it. But before you measure it, it hovers in an uncertain state. And this is called the superposition of 0 and 1. And the Y state has equal amounts of 0 and 1. So when you measure it, it has a 50% chance of being 0 and a 50% chance of being 1. And these different points on the Bloch sphere can have different percentages. But this is the miracle of quantum mechanics. When you are not measuring something, it remains in an uncertain condition. And that makes it possible to do very powerful calculations that you cannot do with bits that are just 0 or 1. You can.
So you're saying that you're saying that it actually is affected by the observable phenomenon?
People, somebody has come back to make background noise on Zoom. Let me figure out how to get rid of it.
So you're saying that
Wait, is that someone actually trying to ask a question? Right? Perhaps I meant.
Yeah, I was asking if you said that it actually is affected by the observable phenomenon. Like when you look at a light ray, it actually changes the observable phenomenon when you measure it.
Yes, absolutely. And this, by the way, is something I've talked about recently before. This is what was invented 100 years ago when quantum mechanics was invented. They observed that light moved like a wave, but when it hits a screen like a CRT, it just makes one bright flash. It only hits one place. So when it moves, it smears out across space like a wave. But when it arrives, it always arrives at only one point. This is the way the world really is, and it is really strange to get used to. In the normal world we live in, if you have something like a baseball and you throw it, it always is in a place. Even all the way along, it's only in one place. It doesn't blur out. But electrons and lights do, and all kinds of, and really all the fundamental particles do. The only reason baseball don't is because it's got a lot of particles, and that's enough for the statistical variation to cancel out.
But isn't it the same thing with the baseball that you can either know its speed or you can know its location, but you can't know both its speed and its location at the same time?
Yes, in principle, that is true. But in practice, because you have an enormous number of particles and you calculate the average, that randomness gets very small to be essentially unmeasurable.
Gotcha.
Yeah. But that's why. So there's this magical thing called measurement, which causes things to stop being uncertain. But while they're uncertain, if you think about it, a normal bit only has one bit of information, 0 or 1. But this qubit has a lot more information, like 2 floating point numbers, this angle and that angle. So there's a lot more information in a qubit. And so a calculation done with a group of qubits is much more powerful than a calculation done with an equivalent amount of bits. But you have different operations that are available on the qubits, and that's what we're going to play with now. So hopefully this thing finished. It did. So if I do nano, let me get what I'm calling, I think P1.pi or something. Let's see. Yeah, Q1.pi. So I'm going to put in this code and we're going to run it and make a qubit. So nano Q1.pi. All right. I put in my Python code and I'm going to run it. Python, make this bigger. Q1.pi. In fact, I can probably make it higher on the screen too. Be better for projection in the room. There. All right. So when I run it, it creates these simulated qubits, and there we are. And so it just prints out 10 zeros. And if you look at the code, let's cat it. It's not listening to me. Cat Q1. Okay. So if you look at the code, it is created. It just created qubits. Allocate qubit just creates a qubit, and by default, the qubit starts in the state of 0, no uncertainty, and then it just measured it. So it, of course, got a 0 for every measurement. This quantum engine flush is what you have to do before you print it for some reason. And so this prints the value of the qubit is just 0, and every time you do it, it's 0. You can do it over and over, it will always be 0. So that's not very exciting, but that just gets you to see how the libraries are used and such. So let's go on to Q2, which is here. Okay, and there. So if I nano Q2, Q2.pi, and I put in this code, this time, let's see, I got to use this. All right. So now I just import the same libraries, but now here I'm, wait a minute, something weird is going on. I've got weird stuff that shouldn't be here. Let's get Control XN. Well, I probably copied too much junk from the web page. Let me shrink my font a little. No. Oh, this just makes 2 qubits, one in state 0 and one in state 1. All right, fair enough. I just thought that was a little too simple, but apparently it's all right. All right, so let's nano Q2. Okay, put in that code. All right. So here, after I import the libraries, here I create a qubit in state 0, and I measure it, so it's going to be 0. And then I'm 10 times going to put it in a state 1. And the way I did that is by rotating with the X rotation. And that's what this diagram shows you. These are the transformations that are available. An X operator rotates it by 90 degrees about this axis. Or no, 180 degrees about this axis. So an X operation rotates a 0 into a 1. So you move from one certain state to the other certain state. So again, there's going to be no randomness here. So I save this and I do Python Q2.pi. And so the first qubit is always in state 0. The second qubit is always in state 1. These are the bits you use in normal digital computing, just these two, always 0 and always 1. And those, so far, we're just reproducing the same thing a normal computer does. But now we're going to move into the world of superpositions. This is called superposition state, where you enter a state that is partially 0 and partially 1, because you're at an angle on that block sphere. So this is Q3, nano Q3.pi. All right. And so the way you do that is, here I have a qubit, and I'm first going to start with all of them in state 0. And then I'm going to make ones in superposition state. So I create a qubit and then I use an H operator. And an H operator stands for Hadamard or something, but the H operator is what rotates it to this other angle halfway up. This one, the H operator rotates it 90 degrees down to here. So now it's in an uncertain state that is partially 1 and partially 0. And we print out 10 of them. So if you run this, Python Q3, right, the original normal state is always 0. The superposition state is sometimes 0 and sometimes 1, with a 50% chance of either of those when you measure it. Okay, now we can now make a circuit of these things with several qubits. So we're going to set up 2 entangled qubits here. And now with normal bits, your operations are things like XOR and NOT. That's what digital computers have, with transistors. They have ones and zeros, and you can do a NOT that changes a 0 to a 1, and you can do an and you can do an XOR, and then make truth tables, and that's what all of our digital computing is. It's just those simple operations. And in quantum mechanics, the simple operations are different. So here's Q4. Right? And so here, what I'm going to do, oops, I keep scrolling at the wrong scroll bar. All right, so now I start with the qubits in state 0. And down here, I make the super, wait, this is not right, all right? I must have copied the wrong stuff or something. Wait, I want to not save it. Control C, Control X, N. All right, let's go here and get the right code. That should be entangled. Oh, I had a C not in it. Okay, but maybe I didn't copy it or something because I didn't seem to get that in the here. Let me try this again. Nano Q4, paste. Verbatim input. Yes, that was the idea. What is this garbage? Control V. Command V. There we are. I don't know what's going on. Must be hitting the wrong keys. All right. Whoa. I got some weird extra character there. We'll see if this works. So now I import measure H and C naught. C naught is the operation that entangles qubits. Now I create 2 qubits, qubit 1 and qubit 2. I rotate one of them so it's in an uncertain state, and I connect them by C naught so they are entangled. Entangled qubits always have to move together. This is the process called spooky action at distance by Einstein. It is, you can create this if 2 things are created by the same fundamental operation, like the decay of a radioactive atom, they are entangled. And if one of them has a certain state, the other one always has the opposite state. And in this case, in this mathematical algorithm, make it so that they're always together instead of always being opposite, but amounts to the same thing. So entanglement is one of the fundamental operations. Hadamard is one of the fundamental operations. Rotating by X is one of the fundamental operations. Those are the operations you can do on a qubit. And so this one here, if I run this one, Python Q4, then there's a pair of them. And the first one is random. So it's sometimes 1 and sometimes 0. But the second one is always equal to the first one. They always get pairs of numbers that are the same. So that's quantum mechanical entanglement, which is one of the essential relationships to make quantum computing things run. And you can make circuit diagrams that show what's going on here. And here's the code that does that. And this is going to be, what do I call this? Q5? Yeah, Q5, all right. All right. There we are. And so now you import different libraries than before here. You import circuit drawer and use the circuit drawing engine. Now you allocate qubits. You build the same network with a Hadamard gate rotating the first one to an uncertain state and C naught entangling them so they will always be identical. Then you flush it and then you just print with drawing engine. You make a latex file, which is one form of a pretty graphics of this. So I save this and then run it. And it prints out this stuff. This is latex. So I want to save that in a file. All right, and I don't have a latex viewer, but what you can do, you can view the files in this environment. If you go here, and I can open them in another tab, I've created something called q5.txt, and it should be here. Files. There it is, q5.txt. I can download that file by right-clicking this down arrow and saving it. Yes, okay, goes in my downloads folder, q5.txt. Text, right? Yep, q5.txt. I'll replace it. All right. And now I can convert it to a PDF with an online converter, like which is here. There. Free file convert. So I can convert, get rid of this garbage. I should convert. Yes. Maybe I'll have to use a different browser. Let's try that. For some reason, it's not working in that browser. All right, choose file. Okay, it's working in this browser. All right, a lot of weird problems today. All right, then I choose my output to convert it to PDF. All right, and convert. And it's done. And now it's done. I can download it here. So I can right click, maybe just click this little download. Yeah, saves it and downloads as Q5 1. That'll do. I can find it. All right, now I look at my downloads folder, which is going to be here. Okay, and I sort by date, put the new stuff on top. There it is. What? Nope, it's not there. Did not save it. All right, let's try again. Download. Did I put it somewhere wrong? In the downloads folder, it says it's there, but I can't see it in the other window. What did I do wrong here? This is the downloads folder. Do I have to refresh or something? I'll close it and open a new window. Man, a lot of weird problems today. All right, downloads. There it is. That's the Finder crashing on me. Anyway, here's the PDF. If I double click it, it should open in the PDF viewer on this Mac. All right, preview. And once again, I'm strangely getting no response, probably because some garbage is freezing up there. All right. The viewer is not opening yet. Right click, open with preview. I can open it in a browser. Preview is not going to work. Man, a lot of problems today. Let's go to a browser. All right, there it is in a browser. And there it is. Very slow, but there you can see it. There it is. So this is the incoming qubit in state 0 going through a Hadamard gate and then being connected with entanglement, which is expressed by this symbol. So these two are, that's what the diagram is that goes with this. Let me go back and see if any part of anything is working for me. All right. All right. So that's a very simple circuit with just 2 qubits. So now we're going to make one with 3 qubits. And we're first going to start with the pretty picture of it. So I go here and I make the file nano demo a .pi. All right. This is the code that's going to do it. You see, I've got 2 Hadamard gates and an entanglement here and 3 qubits. So I'm going to run this and I'm going to run Python, this one, demo A to demo A. All right. Oh, I missed the first letter in my copy and paste. I often do that. All right. All right, that should create a file called demo.a.txt. If I go to the file list and refresh it, there it is, demo.a.txt, and it's 2 kilobytes, which is how big these text files are. So I save that in downloads. Okay, that's demo A. Now I'm going to try to convert it. Perhaps the file converter will not work in this browser. Let's try it again. Nope, the file converter does not work in that browser. Let's go to the other browser where it works. Very strange how only a few actions work, but I'll just work with the few things that are working. Choose file. Okay, demo a.txt. Convert to PDF. All right, convert. And there it is. Okay, download. Put it in downloads, save. And there it appears up here. That's handy. There, demo a.pdf. Now, if I double click it, I wonder if I can do that yet. Nope, looks like double click is broken on this Mac for some reason. Lots of things are broken today, but dragging it into a browser is not broken. So I can zoom in, should be possible. There we are. So here's what we've got. I have qubits 1, 2, and 3, and I've entangled 1 and 3, and I flipped 1 and 2 to an uncertain state, but it's not connected. So it's an interesting circuit, and it might not be too obvious what it's going to do, and the diagrams do not show you what it's going to do. Now I see a chat message, missing P on the first line. Correct? You're right, you got that. Okay. Anyway, now we're going to see the results of this, and you need different code for that. You need to import different libraries and such. So if I go to here, here's the code that imports the main engine, not the drawing engine. And now I allocate the qubits, I make the same circuit, and now I measure them, flush and print the value, and then I put it in a loop to do that 10 times, because there will be some randomness, and I want to get a feeling of the variation. So this will be the other file, which I'm going to call nano demo B. There. All right. Let's see if I can get to the start. This should do it, escape backslash. Yeah, I got the F this time. All right, just save this and run it in Python. Demo B. All right. That's there. It ran it 10 times and printed the results you see. So notice the first one and the third one are always the same. Sometimes this is 0, but if this is 1, that's always 1, because those are entangled. The one in the middle is randomly 0 or 1, and it's not connected to the others. So that's what that circuit does. It connects these two are entangled, this is not entangled, and there were therefore 4 possible results. The first and third can be 0 or 1, and the one in the middle can be 0 or 1, and that's it. 4 possible possibilities. 111, 000, 101, and 010. So that's what you get out of that circuit. And so there are some challenges. You can program a circuit that matches this diagram, and then you can run it and find the answer that has the largest number of ones to be the flag. And there's one where you make a 5-qubit circuit, and again, calculate take that 5 bits, interpret it as binary, and get a number. So you can practice these things. Now, these are just simple demonstrations of what these fundamental operations do. To understand why we care about this, we bring up Shor's algorithm. This is the one that matters most to us. Shor's algorithm is the algorithm that will crack RSA encryption in quantum computers in principle. And there should be a diagram of it in here. There we are. There's a diagram of the circuit. So now you have some idea what these symbols do. This is what you have. You have Hadamard gates on these inputs, and you have entanglement at these points. And this does a thing called the quantum Fourier transform. And so by feeding in a pattern here that you get from the composite number, P times Q, you can get an output here, which will determine one of the factors. And it can do it in very short time, but it requires a large number of qubits, and they have to be very accurate. So they are not noisy, and so the entanglement is very accurate. And right now, the quantum computers don't have enough qubits at all, and they're too noisy and too inaccurate by far. So quantum computers will have to get like 1,000,000 times better than they are before they can crack like a 1024-bit key here. But that's expected as they keep improving, and we expect it to go like Moore's law. So probably in a couple decades, they will be powerful enough, and that's why we're all moving away from this kind of public key encryption. So that's the quantum thing I wanted to show you. Let me see if there are more comments in the Zoom. I think there are not. There might even be comments in the Twitch, I suppose, if anybody's able to get Twitch working today. But there aren't. All right, good. So I'm going to stop this recording.